Welcome, everyone. Very excited for today's session. My name is Brandon Royal. I am a product manager on the GKE team, and welcome to this session, Untrusted Code and Unprecedented Speed, High-Velocity Runtimes for AI Agents. Really excited for this session. We're going to go pretty deep into really what it takes to build infrastructure for today's AI agents. No doubt through the course of the last couple of days, you've heard all about AI agents, running AI agents, AI models, the runtimes themselves. We're going to talk about some of the underlying infrastructure that makes a lot of that possible and how you can leverage that infrastructure for your agents. Again, my name is Brandon Royal. I am a product manager, as I mentioned. I'm joined by Jeremy, who's going to be taking the stage here momentarily, as well as Eric from our partner and customer LangChain. So agents have evolved quite a bit over the last few years. They've evolved incredibly fast compared to typical evolutions of technology. Not all that long ago, we had things like function calling. We were really excited about this idea that we could actually have an agent call a function and do something, right? And then we had MCP, and MCP would solve all the things, right? We can interconnect these systems. We can sort of manage context with tool calling. And then we said, OK, well, we can take this a step further. We can do things like computer use. We can give agents browsers. And then we realized, oh, wait a second, these agents or the models themselves are incredibly good at coding. What would it mean to actually have a coding agent? And things like Claude Code and Gemini CLI, they really paved the way for doing long-running coding agents. And then now you're seeing these persistent agents. So now we're not using an agent for one particular task. We actually have an agent that's running 24/7, right? If you look at what OpenClaw is doing as an example. And so in order to support this evolution of agents, agents need more than just the intelligence. And hopefully that's pretty obvious for folks that are looking at this space. It's more than just a model that is very capable. We need systems and compute that can do the orchestration, that can do the execution of code, of terminals, of browsers. We need all the coordination of the context between the tools and the LLM and potentially even multiple agents that are working together. And then all of that value that's being generated by the LLM, well, that also needs to be served, provided back to users. So we need a compute environment that can support all this. So, in the last several months, excuse me, we've had sort of this coalescence around this word of agent harness. So the agent harness essentially represents now that compute environment that can do a lot of these things. So if you take the intelligence and then you add it to the compute environment, now you have the full infrastructure needed for a modern agent. And so that's what we're going to talk about. So TLDR, you are in the right place. Thank you, by the way, for walking so far. I realize this is at the end of the hall, so thank you for being here. We're really excited. You are in the right place if you are building agent systems at scale. So if you're thinking not about one agent or two agents or three agents, but hundreds of agents, thousands of agents, millions of agents, you're in the right place. If you want to understand some of the considerations for AI agent runtimes and infrastructure, now you'll also hear how sandboxes are a very much core primitive of agent runtimes and harnesses. And so we'll talk a little bit about the sandbox and the role that that plays. We will talk a little bit about Kubernetes and how it really strikes a perfect balance for agent platforms and builders. But it does have some gaps, and we'll talk about those gaps and how we're filling them. And then we'll talk finally about some of the major investments that we're doing for things like sandboxing, for kernel isolation with gVisor, and pod snapshots and much more. OK, so let me give you maybe a bit of an example of how quickly things have changed. All right, went a little too fast there. So I'm, air quotes, the old way, right? The old way, we'll say 2025, you had, an MCP server. So let's say I wanted, as an example, I wanted to integrate with a new service, whatever that happened to be. I would sort of wrap my existing service, my API calls, in something like an MCP endpoint. I would have to think about integrating API keys and doing auth and all that. I would have to build and test that code, right? The MCP service, that wrapper is still code after all, so I need to build and test it. I need to register it with an MCP server. I need to deploy it as a service, and I'd have to repeat this every time. Every time I'm making an API change, I have to do this for every one of my services, which, again, last year we were really excited about that. But if we look at what agents can do today, if you take skills and code execution, you can take what took hours of humans to develop into seconds. So now I can take, integrate a new service. I can say, hey, agent, or hey, LLM, I want to do this thing, help me to do it, give me a skill, and that skill can essentially execute the code in the right runtime environment and achieve the exact same outcome in seconds. So hugely, hugely powerful. It's also hugely, hugely dangerous if we don't think about this, right? If we don't think about, well, what does it actually mean to integrate with that environment? How do we ensure that whatever is being executed in that runtime is fully isolated, both at the kernel level and the network level? We can get ourselves into trouble. So with great power comes great responsibility, and that's what we'll talk a little bit about. Now, if we look at the use cases, so we have code execution tools, things that have been around for quite some time. These tend to be very short-lived. We have things like computer use agents, terminal use agents, things like that. These are achieving like a specific task, like a coding agent as an example, and typically have a bit of a human-in-the-loop kind of model. So do some work, ask for clarification from the user, come back. And then we have our sort of persistent agent, which is the one that we've evolved to in the last couple of months, where we have things like OpenClaw. We're running these things literally 24/7. And so for all of these cases, we need to have absolute kernel-level isolation. We cannot run these things in an environment that shares kernels with anything else, just because of zero-day vulnerabilities and escape vulnerabilities and things like that. We also need to, of course, have network isolation. In the cases of code execution and computer use agents, we need to have very, very low latency. And we're talking about 500 milliseconds or less low latency for a lot of these cases. And then we need to also think about snapshotting. So maintaining the state of the agent means we actually have to also maintain the state of the runtime environment. So whatever is in memory, what is being written into the file system and things like markdown files, these all need to be persisted, and we need a snapshotting mechanism, whether it's snapshotting for doing forking, so if we're running multiple parallel processes, or whether it's snapshotting to do rapid suspend and resume. This is now a core infrastructure primitive that we need to provide. And then we need massive scale. Now, again, hopefully you all are here because you care a lot about scale. You're looking and saying, okay, we have lots of powerful use cases that we can take advantage of agents for. We are going to need the level of scale that the infrastructure can provide. Okay, so as builders, you now have a wide range of options. Of course, you can use things like the agent platform from Gemini Enterprise. You can build your own compute, right? So you can take VM instances and you can build up this runtime environment, of course. Or you can kind of fall right in the middle, right? And this is where Kubernetes or platforms like Kubernetes tend to sit, right? This provides sort of the right level of abstraction where you have the control plane that's provided to you. It's very customizable. You can bring your own compute. You can sort of extend it with APIs in any way that you'd expect. So it's sort of that Goldilocks right in the middle. Provides the right level of management and the right level of customizability. So if we look at now those requirements that we just talked about a few moments ago, on the DIY compute side, yeah, you have kernel and network isolation in some cases. Depends on the platform, and there's a little bit of work that needs to be done. In some cases, you do have low latency. Again, it depends a little bit on the compute platform and what your requirements are around low latency. And sometimes you do have snapshotting. You could do full VM snapshotting, as an example. And on the other side, if we look at sort of managed providers provide excellent kernel isolation. So if you're using, again, like agent platform as an example, you're going to get kernel and network isolation out of the box. You're going to get very low latency. You're going to get snapshotting. Those are all built on the same infrastructure that we're talking about today. So you're going to get all those capabilities, but you are going to sort of have to think about scale and extensibility in different ways. So what if we could take that middle column and we could say, all right, what if those sort of gaps in low latency, because again, if we talk about 500 milliseconds or so being the requirement for low latency, what would it mean to actually bring that down quite a bit from the 1 to 3 seconds that it is today in Kubernetes down to sub-second or even sub-500 milliseconds? And then same thing with snapshotting. What if we can actually snapshot the exact state of a running pod, a running environment, the memory, everything that's on the disk? What if we can turn all of those green? So that's what we're going to talk about today. So GKE provides, so we're actually really excited about a lot of the work that we've been doing within GKE and within Kubernetes. We are excited about a new announcement that we're making this week called Agent Sandbox. This is actually built in open source. So it's based on a Kubernetes SIG called Agent Sandbox. We've been contributing to it for the last several months with many of our industry partners. And on GKE, we provide very, very high throughput scheduling with 300 sandboxes per second. And we're able to now do that at sub-second latency. And the really cool thing is we can provide, we integrate with things like Axion, so you can leverage a very price-performant compute platforms directly within GKE, which delivers industry-leading price performance. So really excited about that capability. And then it deeply integrates, of course, with our entire stack. So it's not about just the low latency allocation and the sandbox management for the runtimes themselves. You also have things like agent identity and access control, network policy and control, full governance, full observability, all the way down the stack, including all the way down to the compute layers where you can take advantage of things like our C-series and our N-series compute platforms that are ideal for agent runtimes. And we have some amazing customers that are building on top of our sandboxing stack today. A great example is Lovable. And I think you've heard maybe a little bit about them this week if you've been to some of the sessions. Lovable is building the cutting-edge sandbox, GKE's cutting-edge sandboxing capabilities allow us to reliably scale to hundreds of secure sandboxes per second, ensuring we can seamlessly empower builders even during massive, unpredictable demand. So really excited about the work that Lovable is doing with us on our sandboxing stack. And then you actually hear directly from the LangChain team, who's also using our sandboxing stack for a lot of their core products. And I won't read the whole quote to you. You're actually going to hear directly from LangChain in a few moments. So when we think about low latency, what does that actually mean? So what would it mean to actually have low latency sandboxing, and how does it actually work underneath the covers? Well, we can imagine for a second, we've got a user, and the user says, hey, I need a sandbox environment. This could be a user. This could, of course, be an agent itself. I would then provide say, OK, I'm going to now provide a sandbox environment, and then I'm going to have to wait for that compute environment to be spun up. Best case scenario, we're talking a couple of seconds within Kubernetes. Worst case scenario, we're talking about a couple of minutes. If we need to spin up the actual compute, we need to pull the images, all those things. So it takes a little bit of time. And in some cases, that's perfectly acceptable. But for a lot of agent use cases, we need to go a lot faster. So what would it mean? Yeah, so again, that's 2+ seconds. What would it mean to do this with an agent sandbox? Well, now the difference is user requests a sandbox. We immediately pull the sandbox out of a pool. And then we backfill that in the pool itself. And that allows us to get sub-second, even sub-500 milliseconds, depending on your throughput. This is controlled via a sandbox template, so you can manage it in the same way that you would manage your Kubernetes infrastructure today with the sort of high performance that you can get. Now, the other scenario here is, OK, we've got an agent. A lot of agents, they tend to sort of have their periods of idle and active time, especially these longer running agents or coding agents. So when an agent, for example, is idle waiting for human input, it's just wasted compute. It's not zero compute utilization, but it's at least reserved. And so what would it mean if we could essentially take all of that idle time and then suspend the exact state of the sandbox and then restart it, getting the efficiency? And so in order to do that, just to give you a sense of what that actually looks like, so we have, again, our end user making a request. Now, in this case, we typically route things through something like a gateway. The user kind of says, OK, I no longer need this. It's now in an idle state. What we can then do is we can say, sandbox suspend. And we provide a Python API. You can, of course, do this directly through a Kubernetes API. And we can say, while I'm suspending this, I want to take a snapshot before I actually suspend it. And what that'll do is, using an integration that we call pod snapshots, we can then snapshot the exact state of that running pod. We can store it in GCS. And then when the user comes back and says, hey, I want the sandbox again, we can just essentially do the reverse. We can now say, OK, sandbox resume. And we can pass it a specific ID, or we can say, grab the latest one. And then we can rehydrate that really quickly. Oh. All right, so give you a really quick sense of what that looks like. Try that one more time. There we go. All right, so we got an example. Now, we do sort of normal coding demos. We're going to do one that's a little bit fun and different. So instead of coding agents, we're going to do dog agents. So we've got a bunch of dog agents. They're doing all the things that dogs do, right? But they're running code in the sandboxes themselves. So they're eating, they're sleeping, they're doing all the things, right? And we can see when we run our 4 dog agents here, fly out on the left, we can see how quickly they're created and that they're suspending. Now, we want to do this really fast. So again, the high throughput, low latency scenario that we need for a lot of these agents. Let's imagine that we want to run the simulation one more time. And instead of just 4 dogs, we're going to run 200 instead. So we're going to run this simulation again. Now, and because we're using that warm pool of compute, we're able to spin these up incredibly fast. And so now we're getting up to 200, and we can keep pushing this and pushing this and pushing this as we want to. And you can see that not only do we have all of our agents running, you can see how they're being created and running, we can also see how they're being actively paused. And we're able to do this because we're snapshotting the state of that running sandbox. We're pausing exactly what's happening in the sandbox, including its memory and its file system, and then we're quickly resuming it back. So that delivers significant performance improvement, which I'll hand it over to Jeremy to talk a little bit more about how that works under the hood.
Thanks, Brendan. I'm Jeremy Olmsted-Thompson, tech lead for GKE Compute and AI Platform. And yeah, I'm going to talk a little bit about how this stuff works. So first, isolation. So isolation is definitely not optional with agents, right? You are letting your best developer loose in your cluster, and this developer is getting smarter every month. They can do anything, right? So you want some guardrails on the capabilities that they have. Also, you want to give them access to things, right? They can't just be in a box. You need some control there because they need to be able to reach out and do things. That's the power. So we kind of think about this in two levels. So there's the kernel-level isolation, which actually lets you run the code on a host, on a shared host, and trust that that agent isn't going to be stomping on other agents or other workloads and causing problems there. But then there's network access and isolation, and you want to be able to control what they can talk to. And we rely heavily on Kubernetes network policies for that. Control what they can talk to, and monitor what they can talk to as well, so you can see what they're actually doing. Here we're going to focus more on the kernel-level isolation and that protection, letting you run multiple agents on the same host. So there are many options. You've got micro VMs, you've got full VMs, but I'm going to talk a little bit about gVisor, which is Google's kind of specialized container-native option for sandboxing. gVisor provides basically all the kernel functionality by implementing its own kernel in user space in a container-friendly way while providing a fully isolated sandbox. And this is fully container-native sandboxing. I'm going to talk a little bit more about what that means. But before I do, we use gVisor extensively within Google. It's used by DeepMind for running Gemini-generated code. It's used in a bunch of Google products. It's part of Cloud Run. And externally as well, both customers on GCP and off GCP, because it's an open source platform anybody can pull down and use. And it's a very safe way to isolate your containers. But it gives us more capabilities too, and I'm going to talk about that shortly. But how does it work? So let's focus on the isolation layer. So gVisor, it has a really interesting approach. It's not virtualization. It re-implements the Linux kernel interface in user space, the whole interface. So that's memory management, file systems, network stack, process management, all of that re-implemented. And it uses syscall interception to basically redirect to that user space kernel. And this has a really interesting artifact, which is that creates additional layers of security. So it's not just, it's different than normal nested virtualization in that you actually get these kind of two layers, right? You have two separate kernels that you'd have to break through to compromise the system. You've got the gVisor kernel, and it itself is running in user space in using Linux kernel isolation capabilities to protect the rest of the system. So you'd have to get through those two layers. It is not a filter. It actually fully re-implements everything. It takes syscalls in, and then it makes its own calls out as needed. And it uses a separate, slightly higher trust capability companion process called the gopher, for example, for file system access and things that need a little bit more privilege. So there's these layers of defense there and defense in depth. It is container native. And so that means it's got resource flexibility, supports things like burstable CPU and memory, everything you want to pack a lot of instances onto the same host. And in terms of overhead, it also has some very nice capabilities. Because it's not nested virtualization, it stacks well in a cloud environment, right? Where your sandbox host is itself virtualized. And nested virtualization can add something like 8 to 10% performance overhead. With gVisor, the CPU and memory operations inside the sandbox see no overhead. You get full native performance. The security layer does add additional latency for syscalls, things like that. For most applications, this is not noticeable because most applications are doing I/O and then actually doing things on the data that they load. And for many applications, it's not noticeable at all. And it also works with GPUs with very low overhead. So if you have an application that you're building an agent that needs to actually leverage accelerators, this is a great choice. Now, all of these things come together, and we realized, as with this maturity of this sandbox solution, it actually provides a really good platform for enabling sandbox or snapshots. Sorry. All processes and child containers within a pod live in the same sandbox and are managed together as a unit. Using our own kernel means that we have full awareness of basically everything that's happening in there, all the memory state, all the dependencies, open connections, things like that. Anything that the pod has done where it reaches out, we know. And this means that we can very reliably snapshot, restore, and even copy, which is really useful for scale-out. We'll talk about that in a second. Complex application state. So coming back to what Brendan mentioned before, this is a real test that he ran. Because agents are bursty and we can actually suspend them when they're idle, if we do that, we see a pretty drastic reduction in real CPU and memory usage. So this frees a lot of capacity. Looking on this chart, we see something like 40% reduction in capacity. So you can pack a lot more agents on the same host with this sandboxing technology. So we actually built this originally to accelerate inference. So this is another really cool use case if you're serving your own model. Basically, if you can snapshot right as a server is ready to serve and clone that out, you can get drastic reduction in that time to first token. And so what we've seen now is up to 89% reduction in that time to first token just by cloning existing instances. And this isn't just about inference. This also works for slow loading Java applications or something like that. Like anything that takes a while to bootstrap, you can bootstrap, slowly get it ready, not have to hand optimize, snapshot that state, and clone it out. And I also always want to give kudos to the amazing team that's built this here, because every time I give this presentation, that number gets better. I think last year it was 50%, then it was 70%, now we're up to 89. So pretty impressive results there. So what are snapshots? So they are a policy-based declarative tool for using Kubernetes resources you already use. You have customizable triggers, either on demand via the Kubernetes API or integrated directly into your workload. And you can do that for very precise timing right as they're ready. You get the entire lifecycle stored in GCS, automated by our system. And they're workload agnostic. So you can basically just take this little bit of Python, put it into your workload, ready to go. So what's in it? CPU and memory state, GPU memory, the full file system state, and all open connections. So if you're listening, when you restore, you'll still be listening, ready to serve. And as Brendan mentioned before, we have a very simple Python API you can use to consume these. And it also works through the Kubernetes CRD. All right? Thank you.
All right, hi everyone. My name is Eric Johansson. I'm a deployed engineer here at LangChain. Before we kind of get into some of the details, I wanted to go through kind of a timeline. There are a lot of Langs out there, and so you'll kind of understand really like the logical flow of the products that we developed and why we developed them. In October of 2022, Harrison developed LangChain. As LLMs became more popular, we realized that there needed to be an abstraction layer to actually build agents on top of it so that you could add tools and more functionality to your agent specifically. But as people started to build agents, traditional metrics and traditional logging didn't fit with agentic use cases, specifically because of the non-deterministic nature. And so in July of 2023, we released our commercial SaaS offering hosted on GCP for observability and evals. Now, as complexity grew, we started to notice there were more use cases that were deterministic in nature. Think of supply chain or onboarding, or different components like that where the workflow itself was very deterministic in nature, but people obviously wanted to automate that. And so LangGraph was released to solve that specific problem itself. Now, as people started to build out their more complex use cases in agentic frameworks, they had observability and eval, so they had confidence that when they released them, that they were going to operate the way they wanted to. We realized, obviously, we need somewhere to deploy them. And so LangSmith deployment was released as a runtime to deploy your agents, so that out of the box, you had A2A endpoints, MCP endpoints, and a bunch of other features to actually manage the deployment of your agent itself. Now, we officially released LangChain 1.0 and LangGraph 1.0 in October of 2025, but that was also the release of our newest framework, Deep Agents, where for more long-running agents, for more complex use cases, you want to be able to manage things like context, manage memory, provide access to skills or sandboxes. And so instead of you having to build all of those features out yourself in whatever framework you chose, that was the release of Deep Agents. And today, we're going to spend most of our time talking about deployments and deep agents. So we've kind of heard this similarity today where we talk about, with respect to sandboxes, isolation is a foundational runtime primitive. They need to be ephemeral, they need to be persistent, and we need to be able to give access to certain dependencies. And so you can see here, a sandbox is an isolated micro VM that an agent can use to run code safely. This is obviously really important for if you have agents where they need to maybe generate code or run analysis, from a like Snowflake MCP. You obviously don't want that to run in the same runtime or in the same area that your agent is running. You don't want to give it access to that. So you need to be able to spin up a sandbox quickly, do that analysis, return the results to the agent, and then close the sandbox. Now, Deep Agents is the framework that takes utilization, or that takes advantage of sandboxes in nature, where, again, you can see they're designed for autonomous agents. There's native context management built in so that you don't have to manage context for a single user. Your system prompt isn't trying to manage everything for everyone. You can dynamically load context about the user or their use cases, long-term and short-term memories, as features built into the actual framework, which for, again, more complex use cases, as you roll this out to 1,000, 10,000 users, these features are actually built into the framework itself. Part of LangChain's ecosystem in general is that we are model agnostic by nature. So as models change weekly, daily, you can plug in different models and then, again, test the output of your agent based on that model quality. And then, again, similar to what we talked about earlier, you can code with Deep Agents CLI, very similar to Claude Code. We actually have a CLI that obviously has context of what Deep Agents features are that you can actually build with. And again, all of this is open source, available on our public repos. So sandboxes, again, built on Kubernetes, specifically, again, with GKE and access to it. Every sandbox runs inside its own lightweight micro VM powered by Kata containers on GKE. Again, the specific reason for this being it's much more secure than like a traditional Docker container itself. And so this is actually from a security standpoint. Each execution environment gets full kernel isolation, not just container boundaries. Again, for the exact reasons that Brandon was talking about, this is really important from a security, governance, and performance standpoint. Kubernetes network policies lock down traffic so sandboxes can't reach internal services. And users bring any Docker image and LangSmith handles the rest. Again, from the OpenClaw being really cool, but like for us, for example, we were told 15 minutes after OpenClaw was released that we can't run it because of that security and governance layer. Now, again, why GKE? Our entire SaaS platform is hosted on Google Cloud Platform with GKE as the underlying infrastructure. And again, the reason why we had chosen GKE as our cloud provider was for the built-in sandbox runtimes, its enterprise-grade, managed scaling, workload identity, GCP ecosystem. Our entire SaaS platform runs, we don't have to manage any manual scaling. Auto scaling happens under the background or in the background, whether it's throughput for multiple concurrent users, whether it's for more resource-intensive agents. We don't have to manage any of that self. All of it runs in the background, and it scales for different users, whether they're generating 1 million traces a day or 10 billion traces a month. So that's a big reason why we ended up going with Google Cloud and GKE specifically. And the last thing I'm going to talk about right now is there's a big barrier of entry between building something as a prototype, getting started, and then rolling it out to production. There are a number of tools out there. And we have a bunch of different CLI tools. And so, for example, if you were interested in LangGraph for a more deterministic workflow or deep agents, we have CLI access for both, where we make it really easy for you to spin up a project with, again, example code based on your specific use case. LangGraph Dev, so that would be LangGraph New. LangGraph Dev is actually a graphical representation where you can actually see all of the nodes of your agent and test different runtime configurations. You can manage different state at different points where maybe one node has a specific issue, and LangGraph Dev is a really good visualization tool for you to actually do a lot of your testing. And then LangGraph Deploy. You know, as you start to work in dev and as you have multiple people working on different iterations of an agent, LangGraph Deploy is, again, a single-line command where you can actually deploy it into Langsmith's infrastructure, again, with Google Cloud being the actual infrastructure backing it. And then, again, you can immediately have the runtime available. So we make it really easy for you to spin something up and deploy it. I think that's it for me. If you have any questions, feel free to reach out after, and I'll also be at the booth on our expo floor. Thank you.
Excellent. Hey, thank you, Eric. It's been amazing working with a partner like LangChain. It's actually fun working with them on the community. So all the work that they do in open source, allowing our customers, our mutual customers, to be able to innovate in the open source, but also working with them as a customer. So appreciate the opportunity to continue to work with the LangChain team. So we wanted to sort of wrap things up, talk a little bit about how you can start to move forward with agent infrastructure. But before we do, wanted to do one more demo. And so I want to give you a bit of a taste of what's coming. Jeremy talked about how we're going to continue to push the envelope in terms of performance. And so we'll give you a little sense of some of the work that we're doing and we're going to be releasing very soon in the next couple of months in terms of incremental performance improvements of our agent infrastructure. So in this demo, we're going to show you how to actually run. This is a real coding agent that's running. It's just a recorded video. So we've got basically an agent that's running through building an agentic system, so a bit meta here. So what we're going to do is we're going to have our first agent that's going to be our architect. So you can actually see how that's happening. And as soon as that architect is done, what it's going to do is it's going to split that context. It's going to take everything that was done, it's going to clone it using snapshots. And now I have 4 agents that are running with the exact same baseline context. So we have our optimizer, we have someone who's actually doing the code, we have someone who's actually running security. So again, we're using the same baseline context, but we now have specialty capabilities of each one of our agents that are taking that context together. And you can see as soon as the agent is done, it turns gray, which essentially is indicating that we've snapshotted the state and then we've suspended it, meaning it's no longer taking up any CPU or resource consumption. And then finally, we're going to have a reviewer that's going to do sort of a final review of everything there. And you can see each one of the IP addresses. This is an actual pod that's running. So this is fully isolated sandbox infrastructure. This happens to be using gVisor, but of course you can also use micro VMs as well. And we can say, OK, now our lead architect's going to do a final review and see how that one goes. All right. And we can see how the IP address is sort of changing. So these things are sort of being scheduled in one place, being snapshotted, then can be moved to another place very, very quickly. So this is pretty cool, right? This is a cloning kind of scenario, which is quite helpful. But let's imagine we want to scale this up, and we want to scale this up quite a bit. So all right, so I'm gonna scale this up, and we can actually see the same process. We're going to do the same thing, but we're going to do it at massive or much higher scale. And we can see each one of those processes. They're sort of, again, lighting up when we actually have active compute, and then they're turning gray. Essentially, that means we're suspending the state. And you can see on the right side the kind of performance metrics we're able to get. So we're now able to do things like 280 seconds or so of restore time. We're able to suspend it in about 100 milliseconds. And in terms of compute efficiency, you can actually see the kind of reduction that we're able to get. Instead of having all of these agents running and consuming compute all the time, by rapidly suspending and resuming those agents, we're able to reduce our compute by upwards of 90%. All right? And we can continue to push the envelope and push the envelope. We'll kind of let this run here in the background. But hopefully you can get the idea of the kind of scale and capability that we're able to get with things like suspend and resume and integrated sandbox infrastructure. So all of this is being built in open source, and we are really excited to continue to collaborate with the community and build out sandbox infrastructure on Kubernetes. So for getting started. So there's lots of great resources, so highly encourage you to check out some of the stuff that Eric was talking about on the LangChain side, lots of great open source work. Also encourage you to check out some of the capabilities and documentation and labs that we have. On the left side, we have a hands-on lab. So if you want to build any of the stuff that we're talking about today, building on Agent Sandbox, which is our open source project, build on Agent Sandbox on GKE, so the managed version of Agent Sandbox on GKE, integrate with things like snapshots to do rapid suspend and resume. All of that is available directly in the code lab, and highly encourage you to go check that out. Also encourage you to check out our documentation, which goes through that in a lot of detail. And then, of course, we want you to contribute to the open source. So we have a very active open source community around a lot of these primitives. And so this is all in Kubernetes SIG, and would love for you to contribute there as well, if you're interested.